Okay, in the last class we had looked at basically the NC rating, which is using sound pressure measurements in a room from 63 to 8000 hertz. We are going to look at the NR, which is an ISO developed rating called a noise rating curves, which is very similar to the idea is basically very similar to that of an NC rating. But instead of 63 to 8000 we use 31.5 to 8000, and here is a table that shows you so as in the case of NR, you will see that whether you have a NC or an NR, you will see that at 1000 hertz the value, so NR 50 typically will mean that the rating has a value of 50 dB at that particular level, right? And then these corrections are basically based on somewhat similar to the hearing that you have, A weighting that you have, right? Somewhat similar to that. Now again the values define limits of octave band spectra that must not be exceeded. So just like the previous case in the NC rating, we said NC 45 means that it should not intersect the sound spectra from 63 to 8000. So a very similar calculation here. Let's see an example here. So this has so you can see that 58, the lowest curve not touched by the spectrum is 60. So you could say NR 60, or very somebody has can interpolate and say that's NR 58, and this should not be NR 45. That should be NR 60 rating. So again the recommended values are very similar to what we looked at in the case of NC. NR 25 means typically concert halls, broadcasting, recording studios, etc. If it's your apartment or your home, hospitals, conference rooms are NR 30, libraries at 35, and then when you go to restaurants and offices and shops, it's at 40. And you can see when I go to a supermarket or a general office, it kind of goes up. Of course, for engineering foundries, it says light engineering works, it is about 60. Alright, so these are some of the ratings that we have, from which you can do this thing. So we'll come back to, in the last lecture I had told you that there are issues with sound pressure level as a metric. We have been using everything up to this point using the sound pressure level, which is typically measured using a sound level meter. Now this has disadvantages. It decreases with distance, which is something that you are all well aware of. So if I am standing right next to the sound source, it is quite loud, and then I walk a few meters away from there, it becomes significantly lower. So therefore you have what is called as a 6 dB drop for doubling of the distance. So this is one issue that you have to deal with. So somebody gives you a number, the number is actually has to be tied up with the distance from the source that you are making a measurement. So this is one issue. Second is, if in a particular place I have 5-6 different sources, the sound pressure level reading cannot tell me which is the dominant source, where the sound is coming from. So this is an issue that you have to deal with. So multiple sources, sound pressure level is not a great way to do this thing. Also there is something called directivity, which means that for the same distance, depending on where you are, so if you imagine walking around a circle, so at some particular angle it may be quieter, and at some other particular angle it may be louder. So this is called directivity. So therefore using this as a way to make product comparisons become very difficult. So somebody says I have measured sound pressure level and my product is quieter, unless they say that it is at the same distance and there is no directivity issue. So all of these things we have to look at before we decide this thing. So if I want to avoid all of these issues, I have to make these measurements basically in an open field or free field kind of environment. Free field means no reflection. So people create what are called as hemianechoic or anechoic chambers. So we will look at a picture of a typical hemianechoic chamber. So this is for testing basically a truck. You can see the truck chassis. Fairly large anechoic chamber. These things that you see on the walls are meant to create a free field like environment. The waves come and then get absorbed, so there is nothing that is reflected. So effectively the sound generated from the machine is not reflected back. So this is called as anechoic. So therefore of course this is a hemianechoic because the ground you can see is basically a reflecting surface. A fully anechoic will also have these wedges on the wall, on this floor. So basically, to reflect, to simulate open field, you can test only one object in the chamber. The environment effects are eliminated, but it is very expensive to create such a thing and then test this. So the question then that arises is there a metric that is kind of independent of the environment and distance? So can we, so if I want to do sound pressure measurement, in order to have a high fidelity measurement and something that I can trust, I have to do this in a hemianechoic chamber, but that's too expensive to do. So the question is there a metric that is independent of, so we look at sound power. We will deal with this a little bit later, but sound power basically is sound energy which is radiated by a noise source per unit time, and this happens to be a very good measure for comparison. So this is independent of distance and direction, therefore is a good measure for, so if it doesn't matter if I am at distance of 1 meter, if I am at distance, I am doing the sound pressure measurement typically at 1 meter, 2 meter, these are all issues, whereas sound power irrespective of the distance is supposed to be identical and is also independent of the direction. The way we define this, like LP we defined earlier, LW is 10 log base 10 W, which is the sound power of radiated by the test object, by a reference sound power level. This is 10 to the power of minus 12 watts, picowatt. Okay, so remember that this is the base, and very loud sound, let's say 100 dB, is going to be, if you look at this unit, effectively I will get 100 dB is what? W is 10 power minus 2 watts, right? So 10 power 10, so you get 10 times 10, which is 100. 100 dB sound power is an extremely loud source, and you can see that it is only 10 power minus 2 or about 10 milliwatts. So therefore don't be carried away, you know, very often you will see speakers being rated as 1000 watts PMPO, 500 watts PMPO. This is not the acoustic power rating, because 500 watts will blow you away. You and I will be blasted into pieces at 500 watts if you are alive. So therefore you can see that a very, very loud source is of the order of 10 milliwatts. So 120 dB is basically 1 watt, and then 120 dB sound power is extremely, extremely loud. So therefore the ratings that you see on these loudspeakers that you see in concerts and so on is actually more an electrical rating rather than the acoustic rating that is there. Of course, obviously if the electrical rating goes up, the acoustic rating also tends to go up, right? Now what is the relation between so to measure this sound power, there is a quantity called sound intensity. So this is nothing but sound power per unit area. So I'm kind of looking at if I make a rectangle or a cube of a square of 1 meter square, what is the energy going through that square? That is sound intensity. It has a relation to pressure which is in the far field. Again, all of these we will derive a little bit later. So it's directly related in the far field to sound pressure. You can see intensity is P square by rho C. So therefore it is related to the square of the pressure. And normally this far field means far away from the source, that is typically 3 to 4. Free field means no reflections, far field means far away from the source. Far away usually is in terms of wavelengths, it's about 3 to 4 wavelengths from the source. Okay, obviously when you say 3 to 4 wavelengths, far field is farther for a low frequency wave compared to a high frequency wave. So the time averaged intensity is defined by this 1 by T, P, the pressure times particle velocity. All of these, as I said, we will look at subsequently. I'm just coming in, you just need to know that intensity is the way to do this. So the sound intensity measurement is based on what is called as a 2 microphone pressure measurement. So you saw that we have to measure velocity and pressure. We will say a little bit later we will derive these relationships. So a microphone probe looks like this. So here is a typical probe from B&K, and you can see the two microphones, microphone 1, microphone 2. They are what are called as face-to-face arrangements. The two microphones are seeing each other, and there is a physical spacer. We will see what is the need for excuse me physical need for a spacer, that we will see that shortly. And there are spacers of different lengths. You can see a longer spacer here. This is typically 50 mm. This is a short spacer, 6 mm. This is possibly a 12 mm or something a little more longer. So this is the typical intensity probe which is used. The reason why we have a spacer is because we are going to do the velocity that we want to measure is related to the pressure gradient. So which of course you know from fluid mechanics that when you have flow, for example, velocity is proportional to the pressure gradient. So we are measuring the pressure gradient as a pressure difference between the two microphones A and B divided by the spacing between that. So this is the approximation for the pressure gradient. The velocity is related to that. So the measured intensity is we average the pressure coming from the two microphones to get the pressure reading. Then we take the difference between the two, divide by delta R, which is the spacing between that, to get velocity, and then average this out. One of the great advantages of using an intensity is that I don't have to build a special room. I can go to a factory shop floor and do in situ measurements and get what is the sound power generated from that machine. Now this of course assumes certain things, that as long as the things that are in the factory shop floor are making steady noise, that means somebody doesn't come decide while you are doing a measurement to come and switch off the noise, the machine, right? Then then you don't have the assumption of steady noise while you are making measurements to be valid true. So what is done is that you actually take measurements over an imaginary box which encompasses or encloses the whole source of interest. So this is called as intensity scanning. So here's an example. So here is a kind of a looks like a air compressor or some kind of compressor. So here is the imaginary box in black lines, and then what we do is we do a scanning. So you can see that this intensity probe, this has a air filter. This is you know, to prevent flow noise, we have a foam which is put on the microphones, and then you have the scanning method where you simply scan like this, first vertically, then come down, and then horizontally, come down vertically a little bit, scan again, come down. So you see that I can scan this entire area. I can do scanning. The thumb rule for scanning is typically you can't be too fast, nor should it be too slow. Roughly about 1 minute per square meter. So if I have 1 meter square area that I have to cover, I can scan at the rate of I should be able to do this in about 1 minute. So the scanning is done. There are errors that come from the use of this intensity probe. One of the errors is basically what we call as a finite difference error, and that is dictated. So IR is the actual intensity, IR hat is what we measure, and it is related to this sin k delta R by k delta R. So if we want this error, sin k delta R by k delta R is nothing but a sinc function. You know that when k delta R is very small, the value is almost 1. So you can see that that means I need to have this spacer designed in such a way. K is the wave number, which is 2 pi by lambda. So I need this k delta R to be as small as possible. So you can see here I have plotted the finite difference error. If I use a 6 mm spacer, you can see this is the frequency at the bottom. So because it is 2 pi delta R by lambda, so effectively delta R by lambda will dictate the error. So when I have a small spacer, delta R is small. So over a large frequency range, the error is quite small. So 1 dB error is this line. So you can see if I use a 6 mm spacer, I should up to 5000 hertz, I have very error less than about half a dB. But if I use a 25 mm spacer, when I hit 5000, you can see the error is almost 4 dB. So this is unacceptable, right? So why not use only a 6 mm spacer? So why do we want to even have something manufactured which is 25 mm spacer or 12 mm spacer when a 6 mm spacer will do? So basically 6 mm for a frequency, the probes come with 6, 12 and 50 mm spacers. So the question then is, if a 6 mm spacer gives me the best error, lowest error, why not use that? The reason for that is something to do with a phase error. Now what happens is that remember that when I measure at 2 points A and B, the two microphones, there is a phase difference between A and B. So the phase difference also is given by 2 pi delta r by lambda is my finite difference error, but it is also dictating what is called as a phase error. Now for a 6 mm spacer and a 100 hertz wave, the delta, that is the phase difference between microphone A and B, is 0.64, but if I use a 50 mm spacer, it goes up to 5 degrees. The problem is that when I manufacture microphones, there is an error, but there is a phase matching that is done during the manufacturing process, but it cannot be 0. When they say phase matched, that means they will say that the error in the measurement phase measurement between the two microphones is plus or minus half a degree, let us say. Okay, so plus or minus half a degree is the error. So when you do this measurement, there is a measurement error because of the phase difference between the two microphones. So the phase is estimated only to an accuracy of plus or minus half a degree. Now obviously, if I have a 6 millimeter spacer and I am interested in a 63 hertz wave, the phase difference itself, the actual phase difference itself is half a degree, and your error in measurement is half a degree. Therefore you will not be able to get this phase measured correctly, right? Whereas if I use the 50 mm spacer, the angle is 5 degrees, so half a degree is 10% error, which is somewhat acceptable, right? Therefore at low frequencies, a longer spacer is required to improve phase measurement accuracy. So even though phase matching is done, and the way it is done is basically they will manufacture several microphones, then they will test pairs. So they will find, so that is why it is costly. I remarked somewhere that each microphone is about 1 lakh rupees if you want to buy a single microphone. Now if you want a phase match, because they have to do extensive testing, suddenly instead of being 1 plus 1 2 lakhs, it will be about 3 lakhs, 3.5 lakhs, because they have to actually test several pairs of microphones that they have manufactured and give you the microphone that will meet this plus or minus half a degree. There is another type of probe which is now more recent, which is instead of using two microphones, the intensity is measured by directly measuring the velocity. So it's a micro machined device, and you have two closely spaced heated wires which are exposed to an airflow. So it works on a resistance principle, and this is called a PU probe. One of the major companies is Microflone that markets this probe. So this can also be used nowadays. Now since we have issues with at low frequencies I require a larger spacer, and at high frequencies I require and for finite difference I require a smaller spacer. So you have this conflicting requirement between a larger spacer at low frequencies for phase accuracy and a smaller spacer for finite difference accuracy. So therefore you have people who supply, now you have something called a wideband probe. So what it does is it enables sound intensity, single shot sound intensity to be done. Otherwise what you have to do is you have to carry out one measurement with 50 mm spacer and then one measurement with 6 mm spacer. So the low frequency data you take from the 50 mm spacer, the high frequency data you take from the 6 mm spacer. That means you have to do two measurements. So instead you can buy one of these wideband probes where two spacers and four microphones are used, for example a 25 and a 60, and then you can span 80 to 6300 hertz in one go, right? So this is possible. So this is something that is out there. You can also, so the intensity is actually a vector quantity, which means I measure, when you saw that scanning, it is measured perpendicular to the surface, so you are measuring the power flow in that direction. So you have a vector probe which enables intensity to be measured in three directions, 2D or 3D. So you have three pairs of microphones that come. Alright, so what have we done in the introductory thing? Summary. In the introductory module you have been introduced to, first of all, what is a wave and how are they classified, typical wave phenomena, and then we specifically looked at sound wave and how it was classified, and definition of noise and the need for the estimation of the noise. We saw frequency and amplitude as two characteristics that are very important. I did some sound recordings to show you how a whistle versus clapping has different characteristics, And then we looked at microphone based measurements. How do you select microphones? Then what are objective metrics for sound pressure level using community noise exposure calculations, community noise, subjective metrics such as phones and zones and noise criteria, and NR, which are all related to subjective metrics. And we also briefly looked at the limitation with sound pressure measurements using the sound intensity measurement approach. All right. So with this we will wrap up this lecture and also module 1 effectively. Then from the next video onwards, we will move on to deriving the wave equation, what governs the propagation of waves in air, derive the fundamental equation governing that, look at the solution to that for very specific cases, and then we will see how to apply that knowledge to basically look at different kinds of problems. All right, we will stop here.